The film begins with a cinematic descent into the vast silence of the cosmos, pulling the viewer into the mystery of space itself. The camera sweeps through an empty, starless void, the feeling of isolation palpable as the silence echoes across the void. The infinite expanse of space is framed in such a way that it feels not just empty, but full of unseen forces, moving just beyond the realm of perception. An unbroken darkness stretches endlessly in all directions, giving the sense that reality itself is hanging by a thread, suspended in the unknown. As the camera lingers on a distant, far-off galaxy, the voiceover cuts in, "What lies beyond our reach? What secrets are buried in the fabric of space?" The tone is hushed, the words drawn out, invoking a deep sense of wonder, yet beneath it, there's a subtle undercurrent of fear. The mystery is not just something to be explored, it is something that could change everything we think we know about the universe and our place within it. The camera pulls back slowly, showing the curvature of the universe itself, like a vast, unknowable canvas painted in black, stretching to the edges of comprehension. Space isn't just empty, it is a realm with dimensions we can't fully grasp, filled with phenomena that defy understanding. The vast silence of the cosmos feels like a chilling, cosmic riddle that has existed long before humanity ever looked up at the stars. But despite this, the desire to understand it, to answer the unknown, is woven into the fabric of who we are. We've always looked to the stars for answers, and in doing so, we've uncovered more mysteries, more questions, than we ever anticipated. The music shifts slightly, a haunting, ethereal melody begins to play, evoking both the wonder and the weight of what's to come. What makes the vast emptiness of space so captivating isn't just its scale, but the realization that, even within it, there are forces at work, forces that shape everything we know, and everything we have yet to discover. It's this tantalizing pull between knowing and not knowing that will drive the journey ahead. As the camera moves deeper into the dark expanse, the question lingers, hanging in the air like an unanswered prayer: what secrets lie buried in the fabric of space? In this opening section, the goal is to captivate the viewer with both the beauty and the enigma of the universe. The vastness, the silence, and the isolation create a feeling of awe, but also an undercurrent of unease. This section sets the stage for a deeper exploration of the cosmos, introducing the central mystery that will drive the entire documentary. What do we truly understand about the universe, and what have we yet to uncover? The mystery is not just cosmic in scale but personal in nature, a reflection of humanity's quest to seek knowledge and grapple with the terrifying unknown. As the first chapter, this section must hook the audience by stirring their curiosity, igniting the questions that will compel them to keep watching. Space, at first glance, appears to be an empty, infinite expanse, an endless void between the stars. But as we peer deeper into this cosmic emptiness, we begin to uncover a startling truth. What appears as nothing is teeming with hidden forces and subtle energy. The stillness is deceptive. Beneath this apparent void, space is far from empty. It is brimming with invisible phenomena, stretching and shifting in ways that defy our comprehension. Imagine a seemingly tranquil sea, the surface calm and unbroken, yet beneath it, currents churn and swirl with immense power. This is the reality of space. It is far from the quiet, lifeless void we once imagined. In fact, this nothingness is a seething cauldron of activity, where particles pop in and out of existence, and cosmic energy flows in ways that challenge the very nature of reality. The camera sweeps through the stars, but instead of showing only the visible galaxies, it fades into the invisible, where dark matter and dark energy lurk, unseen yet undeniably present. It's in this hidden realm that space truly comes to life, not as an empty void, but as a vibrant, dynamic field of forces that stretch across the cosmos. In the quantum world, particles behave in ways that seem entirely alien to our everyday experiences. They can be in two places at once, can appear and vanish without a trace, defying the most fundamental rules of classical physics. And yet, these strange events occur every moment, all around us, even though we can't directly perceive them. The very idea of emptiness collapses, revealing that this cosmic void is a stage for complex, unseen processes. At the heart of this paradox lies the concept of quantum fluctuations, tiny, momentary shifts in energy that occur even in the vacuum of space. These fluctuations give rise to what is known as virtual particles, pairs of particles that briefly appear and annihilate each other in the blink of an eye. They are born and die in an instant, leaving no trace of their existence, and yet they shape the fabric of space itself. Even in the absence of visible matter, the universe is not static. The vacuum is alive with these quantum events, pushing and pulling at the very structure of spacetime. As we move from these microscopic phenomena to larger scales, the fabric of space becomes even more surprising. Gravity, once thought to be a force simply acting between objects, is now understood to be the result of the warping of spacetime itself. A massive object, like a planet or a star, distorts the space around it, creating a well that smaller objects fall into. This simple observation opens up an entirely new way of thinking about reality. Space is no longer just the backdrop against which events occur. It is an active participant, shaping the very way matter and energy behave. As the camera pans through the cosmos, we see galaxies spinning, stars burning, and black holes swallowing light, but beneath it all, space itself is contorting, bending, and stretching in ways we're only beginning to understand. The stillness of space is an illusion, masking a deeper, more complex reality. What we once thought was empty is actually filled with hidden forces, waiting to be discovered. And yet, this revelation brings with it an unsettling question. If space is not empty, what else might be lurking just beyond our understanding? What forces are shaping the universe in ways that we cannot yet perceive? The more we explore the fabric of space, the more we realize how little we truly know. Space, it seems, is not an empty stage upon which the drama of the universe unfolds, but a dynamic, ever-changing landscape, filled with mysteries that are just beginning to emerge from the shadows. As we leave this section, the tension between the vast unknown and our growing understanding remains palpable. What we once took for granted as the empty universe is now a place of endless discovery. But this is just the beginning. There are deeper, even more perplexing forces at play, forces that we have only begun to uncover. The story of space is not one of emptiness, but of hidden complexity, waiting to be revealed. And in the silence of the cosmos, the questions continue to grow. What else are we missing? What else lies beyond our reach, waiting for us to finally see it? Humanity's fascination with the stars is as ancient as civilization itself. The night sky, with its glittering constellations and shifting patterns, has always held a mysterious allure, an ever-present, celestial canvas that beckons with questions. From the earliest days, our ancestors looked up at the heavens not only with awe but with the deep instinct to understand, to chart, to explain. The night sky wasn't just a backdrop to life, it was a source of meaning, a mirror to the universe's hidden truths. The earliest known astronomical records date back to prehistoric times. On the walls of caves in southern France and northern Spain, ancient humans painted scenes of the stars, hinting at their desire to communicate with the cosmos long before the advent of written language. These cave paintings, including the famous Lascaux paintings, contain images of animals and geometric symbols, but they also display patterns that suggest an awareness of the stars. They were more than just decorations, they were maps, a way of navigating through the vastness of time and space. Early humans may not have had the technology we do today, but their connection to the night sky was deep, ritualistic, and spiritually profound. The stars were guides, beacons of the divine, or even indicators of the future. But it wasn't just our ancestors in caves who saw the cosmos as something to be explored and understood. In the ancient civilizations of Mesopotamia, Egypt, China, and Greece, the night sky was an open book, and the desire to read it was insatiable. These early astronomers and philosophers mapped the stars and planets, recognizing their cycles and patterns. They saw the stars as more than just distant points of light, they were living forces, expressions of the universe's laws, often intertwined with religious and mythological interpretations. The Babylonians, for instance, understood the movements of the planets with remarkable precision, using this knowledge to predict celestial events. They saw the planets as gods, their movements symbolic of divine will, revealing humanity's earliest attempts to connect the workings of the universe to the rhythms of life on Earth. The ancient Greeks took this quest for knowledge further, shifting from mythological explanations to naturalistic ones. Pythagoras, Plato, and Aristotle all theorized about the nature of the cosmos, proposing that the heavens were governed by mathematical principles. Aristotle, for example, argued that the Earth was the center of the universe, surrounded by concentric celestial spheres. This view persisted for centuries, influencing not just philosophy but also religion and culture. Yet, even in their efforts to understand the cosmos, the ancient Greeks were bound by their limited understanding. They could observe the stars, trace the movements of the planets, and develop complex models of the universe, but they lacked the tools to fully uncover the truths that lay beyond their reach. The greatest leap in our understanding came with the advent of the telescope. In the early 17th century, Galileo Galilei, using this new instrument, turned his gaze to the heavens and forever changed the way we see the universe. For the first time, we were able to peer into the depths of space and see the planets up close, revealing their moons, craters, and distant landscapes. Galileo's observations shattered the ancient geocentric model and confirmed the heliocentric theory proposed by Copernicus. The Earth was not the center of the universe, and the Sun, not the Earth, was at its heart. This moment marked a turning point in human history, as it signaled the end of an era of mythic thinking and the beginning of the modern scientific approach to understanding the universe. However, even as the telescope opened new vistas, it also deepened the mystery. The more we looked, the more we realized how much we didn't know. The stars we once thought were static points of light were actually dynamic, living entities. Galaxies, nebulae, and black holes revealed themselves as the true nature of the cosmos, far more complex and unpredictable than ancient astronomers could ever have imagined. With each new discovery, humanity's place in the universe was simultaneously confirmed and unsettled. Throughout history, our perception of the stars has shifted from divine to scientific, from mythic to mechanical. We have moved from seeing the cosmos as a realm of gods and signs to understanding it as a vast, intricate web of matter and energy governed by the laws of physics. Yet, even as we uncover the deeper truths of the universe, the stars remain as captivating and elusive as ever. They continue to beckon with their ancient mystery, reminding us that no matter how far we've come in our quest for knowledge, we are still at the beginning of our journey. The juxtaposition of ancient myth and modern science underscores the timelessness of our questions about the universe. We are driven by the same curiosity that propelled our ancestors to stare up at the heavens, wondering what lies beyond the stars. As the camera pans across the Milky Way, the viewer is reminded that we are not so different from those early humans, standing in awe of the night sky. We, too, are searching for answers, trying to unlock the secrets that have remained hidden for millennia. And yet, even in the age of telescopes and space exploration, the cosmos continues to hold its secrets tightly, offering just enough to keep our curiosity burning. The ancient connection between humanity and the stars remains, a thread that stretches across time. As we look back on the history of our attempts to understand the cosmos, we are reminded that the mystery is not just something to be solved, it is part of what makes us human. The stars are not just objects of study, but symbols of our endless yearning to know, to explore, to transcend our earthly limitations. And in that quest, we find not only the vastness of space but also the depths of our own desire to understand the universe's deepest truths. The birth of physics marked a profound transformation in our understanding of the universe. Before the scientific revolution, the world was seen largely through the lens of philosophy, religion, and myth. The laws of nature were mysterious, governed by unseen forces that were often interpreted as divine will. But with the advent of modern science, the quest to uncover the fundamental principles governing the cosmos began to take shape, beginning with a man whose name is synonymous with revolutionizing how we see the world, Isaac Newton. Isaac Newton's Principia, published in 1687, was a landmark work that would lay the foundation for classical mechanics. With elegant precision, Newton presented the laws of motion and the law of universal gravitation, principles that would govern not only the motions of objects on Earth but also the movements of planets and stars. For the first time in history, humans had a framework to describe the motion of celestial bodies with the same clarity they used to explain objects on the ground. Newton's laws of motion were deceptively simple in their form, yet their implications were far-reaching. They replaced centuries of mysticism with a system based on empirical observation and mathematical reasoning. Newton's breakthrough was not just about uncovering the forces that govern motion, it was about the very way we approach understanding the universe. Newton's vision of a universe governed by immutable laws, a clockwork universe, became the prevailing model for centuries. Space itself, according to Newton, was an infinite, unchanging backdrop upon which the events of the cosmos unfolded. It was a static, neutral stage, a concept that would serve as the foundation of physics for the next 2 centuries. But while Newton had given us the tools to understand the mechanical world, the deeper mysteries of the cosmos remained just out of reach. Newton's laws were effective for explaining the movements of planets, for predicting the motions of comets, and for understanding the tides. Yet, they were still limited to a world that adhered to the physical laws we could see, touch, and measure. What lay beyond that, in the unfathomable depths of space, remained a mystery. Newton's clockwork universe was mechanical, yes, but it was also impersonal and detached from the chaotic complexities of reality. Then, in the 19th century, the seeds of a new understanding were planted. The Industrial Revolution had opened the door to new technologies, and with it came a new wave of discoveries that would challenge Newton's deterministic view of the universe. The emerging field of electromagnetism, driven by the discoveries of Michael Faraday, James Clerk Maxwell, and others, began to show that forces could act instantaneously across vast distances, not limited to the slow, predictable motion of mechanical objects. Faraday's work on electromagnetic fields suggested that space was not just a void, but a dynamic medium capable of transmitting forces that could influence objects at a distance, almost as if space itself were alive with invisible forces. Maxwell's equations, published in the 1860s, completed this shift, describing how electric and magnetic fields interacted to form electromagnetic waves, which traveled through space at the speed of light. The implications were staggering. Space, it seemed, was not just an empty canvas but a medium teeming with potential. Forces could propagate across it with incredible speed, bending and shaping the very fabric of reality. In this new model, space was not just an empty void, but an active, energetic field in its own right, a fluid, vibrating presence, full of unseen energy. Despite these breakthroughs, something remained elusive. The mechanical world that Newton had described worked perfectly for everything from the motion of planets to the functioning of machines. But when it came to light, heat, and electricity, things became less predictable. The study of thermodynamics, which emerged in the mid-1800s, illuminated this complexity. While Newton had laid the groundwork for understanding energy in mechanical systems, the new science of thermodynamics introduced a far more mysterious concept: entropy. Energy, it seemed, didn't always behave in an orderly, predictable way. Instead, in closed systems, energy tended to disperse, leading to the gradual decline of order, the inevitable march toward disorder and randomness. This stark realization suggested that the universe was not a perfect, orderly machine but a complex, unpredictable system in constant flux. This tension between order and disorder would ultimately lead to the next revolution in physics, the theory of relativity. In the early 20th century, Albert Einstein would bring forth a paradigm-shifting vision of the universe that dismantled many of the assumptions Newton had set forth. Einstein's work, especially his theory of special relativity, shattered the timeless notion that time and space were absolute and unchanging. According to Einstein, space and time were intertwined in a dynamic relationship, a concept that would later become known as spacetime. Einstein's theory of relativity redefined how we understood the very structure of the universe. It suggested that the fabric of spacetime could be warped and curved by the presence of mass and energy. Planets and stars were no longer simply floating through empty space, they were bending and distorting the very space around them. A massive object, like the Earth or the Sun, could literally curve the space around it, causing other objects, like satellites or planets, to follow curved paths. This was not merely a new way of describing motion, it was a new way of thinking about reality itself. Space was no longer a passive stage for events, but an active participant in the drama of the cosmos. Gravity was no longer a mysterious force acting at a distance but a result of the warping of spacetime itself. In this new framework, the universe was no longer a mechanical clockwork, but a living, breathing entity, constantly shifting and changing. Space was no longer the passive backdrop of Newton's universe, it was an active, dynamic stage, shaped by the presence of mass and energy. This idea introduced the possibility that space was far more than we could ever have imagined. It wasn't merely empty, it was full of potential, of possibilities waiting to be discovered. With the theory of relativity, we began to see space as something far more profound than a mere container for the objects within it. The universe itself, as Einstein had proposed, was an intricate dance of space and time, forever stretching and warping under the influence of gravity. The stars, the galaxies, the very fabric of the cosmos, they were all part of this magnificent, interconnected web. Yet, even as we began to comprehend these higher truths, we found ourselves confronting a deeper mystery. The more we understood about the universe's structure, the more we realized how much we still had to learn. And as the camera pulls away from this moment of scientific revelation, one fundamental question remains: what lies beyond the boundaries of our current understanding? What else is hiding in the very fabric of space, waiting to be uncovered? This section traces the evolution of our understanding of the physical world, from the early mechanical models of Newton to the dynamic, ever-changing universe unveiled by Einstein. It highlights the pivotal moments that shaped our understanding of space, time, and gravity, and sets the stage for the deeper, more complex mysteries that await us as we continue to probe the fabric of reality itself. The universe is vast, and yet, its boundaries remain tantalizingly out of reach. Even as our understanding of the cosmos expands, the further we venture into the dark expanse, the more mysteries emerge. Space, once thought of as an empty void, has revealed itself to be far more complex than we ever imagined. But amid the breakthroughs and revelations, one question remains: what is the true nature of space itself? What lies behind the fabric of the universe, the very spacetime that stretches and bends before our eyes. As we delve deeper into the structure of the universe, it becomes apparent that space is not merely a passive backdrop against which the drama of existence unfolds. It is a living, breathing entity, full of hidden forces and untapped potential. At the most fundamental level, space is not empty. It is made up of quantum fields, invisible, fluctuating energy fields that permeate the entire cosmos. These fields form the very foundation of the universe, and every particle, every force, is the result of interactions within these fields. But how do we know this, and what does it mean for our understanding of space? The discovery of quantum mechanics in the early 20th century shifted the entire landscape of physics. With the advent of quantum theory, scientists began to realize that the universe at the microscopic scale was governed by principles radically different from those of classical physics. At the quantum level, particles don't behave like little solid objects. Instead, they exist in states of probability, they can be in multiple places at once, they can be entangled over vast distances, and they can even influence each other instantaneously, defying the classical idea of space as a neutral, static stage. One of the most mind-bending concepts that quantum mechanics introduced was the idea of the quantum vacuum. Contrary to our everyday experience of a vacuum as a complete absence of matter, the quantum vacuum is far from empty. It is a seething cauldron of energy, where particles spontaneously appear and disappear, fluctuating in and out of existence. These quantum fluctuations give rise to what are known as virtual particles, pairs of particles that pop into existence for brief moments before annihilating each other. It is through these quantum fluctuations that space itself is continuously active, even when there is no observable matter present. This realization challenges our fundamental understanding of space, revealing it to be a far more dynamic and complex phenomenon than we could have imagined. But the mystery deepens further when we consider the nature of gravity. For centuries, gravity was understood as a force that acted between two masses, an invisible force that could be explained by Newton's laws of motion. But Einstein's theory of general relativity radically altered our conception of gravity. Instead of viewing gravity as a force acting between objects, Einstein proposed that gravity was the result of the warping of spacetime itself. Massive objects, such as stars or planets, curve the fabric of spacetime around them, creating what we perceive as gravitational attraction. Space, in Einstein's model, was not a flat, unchanging expanse. It was a malleable, dynamic entity, constantly bending and stretching in response to the presence of mass and energy. This concept, though difficult to grasp, suggests that space itself is not a fixed stage, but rather a fluid and adaptable medium that can stretch and contract based on the influence of the objects within it. The more we delve into the structure of spacetime, the more we realize that it is not merely a passive container for the universe, but an active participant in the cosmic drama. Even as Einstein's general theory of relativity has provided a new framework for understanding gravity, the discovery of quantum mechanics has presented a new set of challenges. The theories of relativity and quantum mechanics are, in many ways, at odds with each other. While general relativity explains the large-scale behavior of spacetime, from the motion of planets to the bending of light around black holes, quantum mechanics governs the microscopic world of particles and fields. And yet, these two theories, both extraordinarily successful in their respective domains, cannot be reconciled in a single unified theory. The universe appears to operate under two sets of rules, one for the very large, and one for the very small. This paradox has led scientists to search for a unified theory that can explain both the behavior of the vast cosmos and the subatomic world. String theory is one such attempt to bridge the gap. According to string theory, the fundamental building blocks of the universe are not particles, but tiny, vibrating strings of energy. These strings exist in a multidimensional space, where the extra dimensions of space could help explain the seemingly contradictory nature of quantum mechanics and general relativity. In this view, space itself would no longer be a simple, three-dimensional framework, but a far more complex, multidimensional construct, a place where the very fabric of reality could be understood as a collection of vibrations, stretching, and warping in ways we can barely comprehend. String theory also suggests the existence of parallel universes, or multiverse, where different versions of reality coexist, each with its own set of physical laws. In this scenario, the fabric of space might extend far beyond the universe we can observe, with countless other realities existing in different dimensions, each one hiding behind the veil of our own. This raises the tantalizing possibility that the universe we know is just one of an infinite number of possible universes, each with its own hidden secrets and mysteries. The concept of the multiverse introduces a new layer of mystery to our quest to understand space. What if the universe we see, the one we experience every day, is just a single thread in an endless cosmic tapestry? What if the laws of physics we've discovered so far are just one set of rules in a much larger, more intricate reality? And what does it mean for our place in this vast, potentially infinite multiverse? As we grapple with these questions, we are faced with the realization that space, in all its complexity, may be far more than we can ever fully understand. The deeper we peer into the fabric of the cosmos, the more it seems to stretch and twist in ways we cannot yet fully fathom. The quantum vacuum, with its endless fluctuations, the curvature of spacetime around massive objects, and the possibility of higher dimensional realities, all point to a universe that is far stranger and more complex than we ever imagined. In the end, the nature of space is not just a question of physical laws and mathematical equations. It is a question that challenges the very limits of human understanding. What lies beneath the surface of the cosmos? What secrets does the fabric of space hold, waiting to be revealed? The more we learn, the more we realize that our understanding of space is still in its infancy, and that the true nature of the universe may remain hidden, just beyond the reach of our knowledge. As we continue to explore the depths of space and the mysteries of the universe, we are reminded of our own limitations. We are explorers, standing on the threshold of an unknown frontier, peering into the darkness with curiosity and wonder. But the more we discover, the more we realize how little we know. Space is not just a realm to be understood. It is a vast, enigmatic expanse that invites us to keep looking, to keep questioning, to keep seeking the secrets buried in its fabric. And in that pursuit, we may one day uncover the answers to the most profound questions of all, about the universe, about the nature of existence, and about our place within this boundless cosmos. The shift from the orderly, predictable universe of Einstein's relativity to the strange, unpredictable world of quantum mechanics marked one of the most dramatic intellectual upheavals in human history. Where relativity painted a majestic picture of smooth curves, bending spacetime, and cosmic harmony, quantum mechanics ripped open that serene vision and revealed a realm full of uncertainty, paradox, and bizarre behaviors that defied common sense. It was as if the universe had a hidden side, a second face, lurking beneath the fabric of reality. And when humanity finally glimpsed it, everything we thought we knew about space was thrown into question. At its core, quantum mechanics revealed that the smallest building blocks of the universe do not behave like tiny versions of planets or stars. Instead, they exist in states of probability, where the rules are radically different from anything we experience in daily life. Imagine a particle that can be in two places at once, or a beam of light that can behave both like a wave and a particle depending on how it is observed. This is the strange reality of the quantum world, and its implications reach deep into the very fabric of space itself. One of the most striking discoveries of this realm was the principle of wave-particle duality. In experiments like the double-slit test, light and electrons demonstrated that they could behave as both particles and waves. When unobserved, they spread out like waves, interfering with themselves in beautiful, ghost-like patterns. But when observed, they suddenly behaved like solid particles, choosing a single path. It was as if reality itself changed depending on whether it was being watched. The unsettling question this raised was profound. Does reality exist in a definite state until something conscious measures it? If the act of observation can shape the outcome of events at the quantum level, then what does that mean for space, for time, and for the entire universe? Adding to this strangeness was Heisenberg's uncertainty principle. This principle declared that there are limits to what we can know. Specifically, we cannot know both the position and the momentum of a particle with absolute precision. The closer we come to knowing one, the less we can know about the other. This wasn't a limitation of our tools or technology, it was a fundamental feature of reality itself. Space at the quantum level was not a neat grid of coordinates and trajectories. It was a storm of probabilities, a restless blur of possibilities where certainty was impossible. The universe, at its smallest scales, was not fixed but fluid, uncertain, and profoundly unpredictable. But the most haunting revelation came from the idea of quantum entanglement. Two particles, once connected, could remain mysteriously linked even if they were separated by vast distances. Measuring one would instantly determine the state of the other, as though information traveled faster than the speed of light, violating the very rules set by relativity. Einstein himself famously called this phenomenon spooky action at a distance, unable to reconcile it with his belief in an orderly universe. Yet, repeated experiments have shown that entanglement is real. The fabric of space, it seems, allows for connections that transcend distance, hinting that the cosmos is far more interconnected than we ever imagined. All of these discoveries pointed to a startling truth. The vacuum of space, which once seemed empty, is alive with activity. Quantum field theory revealed that space is filled with invisible fields, vibrating with energy, where particles can emerge from nothing and vanish again in an instant. These fluctuations are not abstract ideas but measurable effects, influencing the behavior of matter and even shaping the expansion of the universe itself. The idea that nothingness is actually seething with invisible activity forces us to reconsider our entire conception of emptiness. The clash between relativity and quantum mechanics further deepens the mystery. Relativity tells us that spacetime is smooth, continuous, and curved by mass and energy. Quantum mechanics, however, suggests that at the smallest scales, space is foamy, chaotic, and full of violent fluctuations. These two descriptions of reality cannot be easily reconciled. When we try to apply both theories to extreme conditions, such as the center of a black hole or the moment of the Big Bang, the mathematics breaks down into infinities and contradictions. It is as if nature is guarding her ultimate secrets, forcing us to accept that our current frameworks are incomplete. This contradiction leaves us standing at the edge of an abyss. On one side lies the grand, sweeping beauty of relativity, on the other, the strange, unsettling chaos of quantum mechanics. Between them stretches a gulf of mystery that science has yet to bridge. The tension between these two visions of reality drives one of the greatest quests in human history, the search for a unified theory that can explain both the cosmic and the quantum, the vast and the infinitesimal. The intrusion of the quantum world into our picture of space forces us to confront an unsettling possibility. Perhaps reality itself is not what it seems. The space around us, which feels so stable and predictable, may in fact be a fragile illusion, held together by processes we can barely comprehend. Beneath its calm surface lies a storm of uncertainty, entanglement, and fluctuation, a hidden realm where the rules of logic bend and the very concept of existence becomes slippery. As the camera lingers on the swirling galaxies and then zooms inward to the jittering dance of subatomic particles, the narrative emphasizes this tension. The universe is both orderly and chaotic, both predictable and unknowable. It is a place where beauty and terror coexist, where the grand architecture of spacetime is constantly intruded upon by the strange, unpredictable world of the quantum. And so, the question remains, what is the true nature of reality? Is the universe ultimately ruled by smooth, elegant laws, or is it built upon the restless uncertainty of the quantum realm? Or is there something deeper, hidden still, that ties both worlds together? The answers remain elusive, but one thing is certain: the intrusion of quantum mechanics into our vision of space has forever changed the way we see the cosmos. It has revealed that the fabric of reality is far stranger, far more mysterious, and far more profound than we ever dared to imagine. For centuries, the universe appeared to us as a grand, luminous display of stars and galaxies, each shining with clarity against the dark canvas of space. Yet beneath that glittering tapestry lies something invisible, something massive, and something utterly essential to the structure of the cosmos: dark matter. It is a mystery that haunts modern physics, a ghostly presence that cannot be seen, touched, or directly measured, yet one that silently shapes the universe on the largest scales. Like shadows that betray the presence of an unseen figure, the galaxies themselves whisper of its existence, bending, curving, and rotating in ways that cannot be explained by visible matter alone. The discovery of dark matter began not with the invisible itself, but with the visible, the galaxies, those vast islands of stars spinning in the void. In the 1930s, the Swiss astronomer Fritz Zwicky noticed something strange when studying the Coma cluster, a massive collection of galaxies bound together by gravity. The galaxies within the cluster were moving far too quickly to be held together by the gravity of their visible stars alone. By all rights, the cluster should have torn itself apart. And yet, it didn't. Something unseen was providing the extra gravitational glue. Zwicky called this invisible component Dunkelmaterie, dark matter. His claim was met with skepticism at the time, but the seeds of a profound mystery had been planted. Decades later, in the 1970s, Vera Rubin, an American astronomer, made another startling observation while studying the rotation curves of galaxies. According to Newtonian physics, stars on the outer edges of a galaxy should orbit more slowly than those closer to the center, much like planets in the solar system orbit more slowly as they move farther from the sun. But Rubin's meticulous measurements revealed something shocking. Stars at the edges of galaxies were moving just as fast as those near the center. The galaxies were spinning in defiance of all known laws of physics. The only possible explanation was that vast amounts of invisible matter surrounded each galaxy, forming an enormous halo that anchored the stars in place. Here, then, lies the great paradox. Dark matter makes up about 85% of the matter in the universe, and yet we cannot see it. It does not emit light, does not absorb it, and does not reflect it. It passes through space silently, invisibly, leaving only its gravitational footprint behind. To detect it is like trying to find the wind in a darkened forest. You cannot see it directly, but you know it is there from the way the trees bend and sway. The implications of dark matter are staggering. Without it, galaxies would simply fly apart, their stars scattering into the void. Clusters of galaxies, too, would dissolve, unable to hold together under the weak pull of visible matter alone. Dark matter is the hidden scaffolding of the universe, the invisible web that holds everything in place. Simulations of the cosmos reveal that galaxies do not form randomly but along vast filaments of dark matter, stretching across the universe like an immense cosmic skeleton. The luminous galaxies we see are merely the ornaments decorating this unseen framework. But what is dark matter made of? This question drives some of the most ambitious experiments in modern science. Physicists have proposed several candidates, such as WIMPs, weakly interacting massive particles, and actions, hypothetical particles that would barely interact with normal matter yet carry enough mass to explain dark matter's gravitational effects. Deep underground laboratories, shielded from cosmic rays, search for the faintest whispers of these elusive particles colliding with detectors. Meanwhile, powerful particle accelerators like the Large Hadron Collider probe the fabric of reality itself, hoping to produce or detect these ghostly particles in high-energy collisions. Despite decades of searching, dark matter has remained stubbornly hidden. No experiment has yet conclusively detected it. Each failure deepens the mystery, forcing scientists to question whether we are looking in the wrong place, or perhaps even asking the wrong questions. Could dark matter be something entirely unexpected, a new form of matter beyond the reach of current theories, or even a sign that our understanding of gravity itself is incomplete? Some physicists have proposed modified theories of gravity, suggesting that perhaps the strange motions of galaxies are not caused by hidden matter, but by an incomplete model of how gravity works on cosmic scales. Yet, time and again, the evidence points back to the existence of something unseen. Gravitational lensing, the bending of light by massive objects, has revealed patterns consistent with vast amounts of invisible matter. Images from the Hubble Space Telescope and other observatories have captured entire clusters of galaxies distorting the light of background galaxies, creating arcs and smears of light like a funhouse mirror. The amount of distortion cannot be explained by visible matter alone. It demands the presence of something more massive, something dark. Dark matter, then, is not merely a theoretical curiosity. It is the invisible architect of the cosmos. Without it, galaxies, clusters, and the large-scale structure of the universe would never have formed. The stars themselves, including the Sun, would not have gathered into coherent systems. In a profound sense, our very existence depends on this hidden matter. And yet, despite its central role, we remain utterly blind to its true nature. This mystery produces both awe and unease. Awe, because the universe has revealed itself to be far stranger and more intricate than we ever imagined. Unease, because it reminds us of how little we truly know. We live in a universe where most of the matter is invisible, untouchable, unknowable, at least for now. We see only the faint traces it leaves behind, like footprints in the sand after the tide has gone. As the camera drifts past luminous galaxies, the voiceover whispers a question. What if the universe we see is only the faintest shadow of the universe that exists? The contrast between the brilliant stars and the unseen dark matter builds a haunting image, a cosmos that dazzles us with its beauty while hiding most of its substance in shadow. And so, the search continues. Each experiment, each observation, draws us closer to the heart of the enigma, yet the answer remains elusive, as if the cosmos itself guards its deepest secrets with silence. Dark matter may be the key to unlocking the ultimate nature of space, or it may point toward an even deeper mystery waiting to be uncovered. For now, it remains the shadowy companion of the stars, the unseen architect of galaxies, and the silent guardian of the universe's grand design. If dark matter is the hidden scaffolding of the cosmos, then dark energy is the invisible force that pulls at its very edges, stretching the universe outward in defiance of gravity. Unlike dark matter, which acts as a kind of glue, dark energy acts as a cosmic accelerator, a force of expansion that seems to grow stronger with time. Together, they form the unseen majority of the universe. And yet, while dark matter remains elusive, dark energy is an even greater enigma, a mystery so profound that it shakes the very foundations of physics and philosophy. The story of dark energy begins with a discovery that shocked astronomers in the late 1990s. For decades, scientists believed that the universe's expansion, set in motion by the Big Bang, should gradually be slowing down under the pull of gravity. Galaxies should be drawing back toward one another, their momentum gradually overcome by the mutual attraction of matter. To test this idea, two independent teams of astronomers began studying distant Type Ia supernovae, massive stellar explosions so bright they can outshine entire galaxies. Because their brightness is consistent, they serve as standard candles, allowing astronomers to calculate cosmic distances with remarkable accuracy. But when the teams measured these supernovae, they found something shocking. The galaxies hosting them were not slowing down. They were speeding up, racing away faster and faster as time went on. The universe was not only expanding, it was accelerating. This discovery earned the 2011 Nobel Prize in Physics, and it introduced a new, mysterious entity into the scientific lexicon: dark energy. What is dark energy? That is the haunting question. It seems to account for nearly 70% of the total energy of the universe, and yet it is invisible, untouchable, and deeply counterintuitive. The simplest explanation ties back to a concept first proposed by Einstein: the cosmological constant. When Einstein formulated general relativity, he initially added a term that would prevent the universe from collapsing under its own gravity, believing that the cosmos was static and eternal. Later, when Hubble discovered that the universe was expanding, Einstein called the constant his greatest blunder. Yet now, decades later, the cosmological constant has returned as a prime candidate for dark energy, representing the energy of empty space itself, a vacuum energy that pushes the universe apart. But this explanation raises as many questions as it answers. Quantum field theory predicts that the energy of the vacuum should be enormous, so enormous, in fact, that the universe would have blown itself apart instantly after the Big Bang. Yet the observed amount of dark energy is staggeringly smaller, off by a factor of 10 to the power of 1 squared compared to theoretical predictions. This is not just a small discrepancy, it is perhaps the greatest mismatch between theory and observation in the history of science. Some physicists call it the worst theoretical prediction ever made. Other theories propose that dark energy is not constant but dynamic, a field that changes over time, sometimes called quintessence. In this view, dark energy could evolve, waxing and waning across cosmic epochs. It might even decay in the distant future, reversing its effect and allowing gravity to reclaim dominance. Still others suggest that dark energy is not a thing at all, but a sign that our understanding of gravity is incomplete, that Einstein's theory, as magnificent as it is, may not be the final word on the cosmos. The consequences of dark energy's existence ripple far beyond physics. Its presence shapes the fate of the universe itself. If dark energy continues to dominate, galaxies will drift ever farther apart, stars will burn out, and the cosmos will fade into a cold, dark emptiness, a fate known as the heat death of the universe. In this scenario, the accelerating expansion will eventually carry every galaxy beyond every other's horizon, leaving each one isolated, a lone island adrift in an infinite sea of darkness. The night sky, once filled with the brilliance of countless stars, would grow empty and silent. But there are more catastrophic possibilities. If dark energy is not constant but grows stronger with time, the expansion could accelerate to such extremes that galaxies, stars, planets, and even atoms themselves would be torn apart, an apocalyptic fate known as the Big Rip. On the other hand, if dark energy reverses or dissipates, the universe might slow, halt, and eventually collapse back in on itself, ending in a fiery Big Crunch. Each possibility paints a different destiny for the cosmos, and we are left to wonder which path we are traveling. What makes dark energy even more haunting is its invisibility. We cannot see it or measure it directly, we know it only through its effects on the universe's expansion. It is like a phantom wind filling the sails of the cosmos, pushing galaxies apart while remaining itself beyond detection. Every observation, every experiment designed to probe its nature, has only deepened the mystery. The more we learn about the universe, the more dominant and inexplicable dark energy appears. And here lies the contrast that keeps the mystery alive. Humanity has built telescopes that peer back billions of years, mapped the cosmic microwave background in exquisite detail, and measured the motions of galaxies across vast distances. We have uncovered so much about the universe's history and structure, yet the majority of it, the very force shaping its destiny, remains invisible and unknowable. It is as if the cosmos is playing a grand trick, showing us just enough to tantalize us, while keeping its deepest truth veiled. The philosophical implications are as staggering as the scientific ones. If most of the universe is made of something we cannot see, touch, or even fully conceptualize, what does that say about our quest for knowledge? Are we explorers standing at the edge of an infinite ocean, staring into the darkness, aware that what we know is dwarfed by what remains hidden? Or are we children deciphering only the surface of a deeper truth, one that may remain forever beyond human grasp? As the scene shifts, the camera pans across the great cosmic web, showing galaxies stretched along filaments of dark matter, while an invisible hand, dark energy, tugs at the threads, pulling them farther and farther apart. The voiceover lingers: if dark matter holds the universe together, then dark energy tears it apart. Between them lies the balance of existence. And the question remains, which force will prevail in the end? In the silence that follows, the viewer is left with a haunting awareness. The cosmos is ruled by forces that remain beyond our comprehension. The stars we see, the galaxies we map, the matter we study, all of it is but a small fraction of reality. The rest is shadow, invisible and elusive, buried deep within the fabric of space itself. Black holes are among the most terrifying and awe-inspiring objects in the universe, and they serve as gateways into the deepest mysteries of space. They are born from death, the collapse of massive stars that fall inward under their own gravity until they crush themselves into a point of infinite density, a singularity. Around this singularity lies the event horizon, the boundary beyond which nothing can escape, not even light. To encounter a black hole is to face the very edge of reality, a place where the known laws of physics shatter and the fabric of space and time is ripped apart. In the vast darkness of the cosmos, black holes lurk unseen, devouring stars, bending light, and warping time itself, silent predators hidden in the void. The concept of a black hole once seemed like pure science fiction. In the early 20th century, solutions to Einstein's equations of general relativity hinted at the possibility of regions in space where gravity became so strong that escape was impossible. At first, these solutions were dismissed as mathematical curiosities. But as astronomers studied the skies more closely, evidence began to emerge. Strange stars orbiting invisible companions, X-ray emissions from compact sources, and, eventually, the breathtaking image of the supermassive black hole in the galaxy M87 captured in 2019 by the Event Horizon Telescope, all confirmed that black holes are not only real, but fundamental to the structure and evolution of the universe. What makes black holes so compelling is the way they bend and twist the very fabric of reality. Near the event horizon, time itself slows to a crawl. To an outside observer, a falling object seems to freeze at the edge, never quite crossing, its light stretched into a red, fading glow. To the object itself, however, the fall continues unhindered, plunging into darkness. This contradiction, where reality depends on your perspective, reveals the strange, malleable nature of spacetime around these cosmic monsters. The black hole is not merely a void, it is a laboratory where the universe exposes its most extreme secrets. But the greatest mystery of black holes lies at their heart, the singularity. This is a point where density becomes infinite, where the curvature of spacetime becomes immeasurable, and where the known laws of physics collapse. General relativity, so successful in describing the cosmos on large scales, simply breaks down in the face of this infinity. To understand the singularity requires the merger of relativity and quantum mechanics, a unified theory that has so far eluded us. Black holes, then, are more than cosmic monsters, they are clues, perhaps even gateways, to a deeper understanding of the universe itself. The paradoxes of black holes extend even further. In the 1970s, Stephen Hawking made the startling prediction that black holes are not completely black. Instead, quantum effects near the event horizon cause them to emit radiation, now known as Hawking radiation. Over unimaginable timescales, this radiation would cause black holes to evaporate, disappearing into nothingness. Yet this raises the infamous information paradox. If black holes eventually vanish, what happens to the information contained within the matter they consumed? Physics dictates that information cannot be destroyed, yet black holes appear to obliterate it, leaving us with a contradiction at the very heart of reality. This paradox ignites one of the most heated debates in modern physics. Some suggest that information is somehow preserved in subtle patterns at the event horizon, encoded like a hologram. Others propose that the very nature of spacetime is more exotic than we imagine, that reality itself is woven in ways we do not yet understand. Each attempt to resolve the paradox pushes us closer to a theory of quantum gravity, the long-sought unification of the large and the small. And thus, black holes, once thought to be cosmic vacuums of destruction, now stand as potential doorways to the ultimate theory of everything. Beyond the science, black holes capture the imagination in ways few other cosmic phenomena can. They embody both creation and destruction, terror and wonder. They are the destroyers of stars, swallowing entire suns in their silent hunger, yet they also power some of the brightest phenomena in the universe. Quasars, brilliant beacons that can outshine entire galaxies, are fueled by supermassive black holes at their centers, devouring matter and spewing out jets of energy that stretch across millions of light-years. In this way, black holes are paradoxical engines of both darkness and light, annihilation and creation. The emotional power of black holes lies in the contrast they represent. To approach one is to approach nothingness itself, to face a horizon beyond which lies only silence and erasure. And yet, in studying them, we uncover the most profound truths about reality. They are both tombs and gateways, endings and beginnings, symbols of cosmic death and hints of deeper, hidden laws. As the camera drifts into a visual depiction, we see stars torn apart by the gravitational tides of a black hole, their gas spiraling into a brilliant accretion disk, glowing hotter than any furnace on Earth. Light bends and twists, forming eerie rings as photons struggle to escape the gravitational abyss. The soundtrack grows haunting, a low, resonant hum as if space itself is trembling under the weight of the singularity. The viewer is pulled into the unsettling realization: this is not merely an object, but a boundary of knowledge itself. And so, the voiceover asks the haunting question: what lies beyond the horizon of a black hole? Is it the end of reality, or the beginning of a deeper truth we have yet to comprehend? In that single question rests the tension between fear and wonder, annihilation and revelation. Black holes remind us that the universe is far stranger than our minds can easily grasp. They reveal the fragility of our theories, the limits of our perception, and the staggering depths of the cosmos. In their silent darkness, they conceal secrets that could rewrite the laws of physics, perhaps even redefine our understanding of space and time itself. They are not merely buried in the fabric of space, they are the fabric's deepest tears, waiting to be unraveled. Time is one of the most familiar aspects of our lives, yet in the presence of space it becomes one of the most mysterious. We count its passing in seconds, minutes, and hours, mark our lives in days and years, and experience its steady flow as the rhythm of existence itself. But physics reveals that time is not a constant, not a universal river flowing at the same speed everywhere. Time is elastic. It stretches, it bends, and it even slows to a crawl depending on the presence of mass, motion, and the curvature of space. When we study time alongside space, we discover that the two are inseparable, woven together into a single fabric, spacetime. And in this fabric, the ordinary and the extraordinary blur into one. The story begins with Einstein's theory of relativity, which shattered the old, absolute view of time. 4 centuries, Newton's clockwork universe reigned supreme, in which time ticked forward at a steady pace, unaffected by anything in the cosmos. But Einstein showed that time is relative, it flows differently depending on speed and gravity. To someone traveling near the speed of light, seconds stretch into minutes, hours into days. To someone standing near a massive object like a black hole, time itself slows compared to a distant observer. This effect is not just theoretical. It has been measured with clocks on satellites and airplanes, confirmed with breathtaking precision. Time, then, is not fixed. It is pliable, malleable, bent and shaped by the universe itself. The phenomenon of time dilation introduces a haunting sense of dislocation. Imagine 2 twins, one remains on Earth, while the other embarks on a journey near the speed of light. Upon returning, the traveling twin has aged far less than the one who stayed behind. This twin paradox reveals the unsettling truth that time is not universal. It does not pass equally for everyone. Each observer, depending on their journey through space, experiences their own personal flow of time. Reality, then, is not one single shared moment, but countless overlapping timelines, each carved into the fabric of space. Nowhere is this effect more dramatic than near black holes. As you approach the event horizon, time slows so dramatically that to an outside observer, you would appear frozen at the edge forever, while you yourself would plunge forward in mere seconds. This strange contrast between perspectives forces us to confront the question: what is time? Is it a fundamental part of the universe, or is it an illusion born from the way we perceive change? Cosmology offers an even deeper riddle. When we look at the large-scale structure of the universe, we see that time itself has a direction. It flows forward, from past to future. This arrow of time is deeply connected to entropy, the tendency of systems to move from order to disorder. A broken glass does not reassemble itself, a star that dies does not reignite in reverse. The arrow of time marches forward, driven by the universe's expansion and the relentless growth of entropy. But physics at its most fundamental level, the equations of relativity and quantum mechanics, do not demand this arrow. They work just as well forward or backward in time. So why, then, do we experience time as a one-way journey? This paradox cuts deep into philosophy as well as science. Is the arrow of time a true feature of reality, Or is it a consequence of the initial conditions of the universe, the Big Bang setting everything into motion in a way that gave rise to the flow we perceive? If the latter, then perhaps time is not fundamental at all, but emergent, a property that arises only at certain scales, like the surface of water emerging from countless individual molecules. In this view, time itself may dissolve at the deepest levels of reality, leaving only a timeless sea from which our experience of past, present, and future arises. Einstein himself once wrote that for those deeply engaged in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. This haunting statement resonates in light of modern discoveries. If time is not absolute, then perhaps the past still exists in some sense, as does the future. The universe could be a vast, four-dimensional block of spacetime, where every event, from the birth of a star to the choices we will make tomorrow, already exists. We merely experience it slice by slice, moment by moment, like reading the pages of a book one at a time. This block universe interpretation unsettles our deepest intuitions about free will and destiny, raising questions that cut to the heart of existence. The practical consequences of relativity and time dilation already affect our lives. GPS satellites, orbiting high above Earth, experience time at a slightly different rate than we do on the surface. Engineers must account for both gravitational time dilation and the effects of high velocity to keep the system accurate. Without Einstein's corrections, GPS would drift by kilometers each day. In this sense, the bending of time is not a distant curiosity but a tangible part of modern technology, a reminder that our everyday world is already shaped by the pliable nature of time. And yet, the mysteries deepen. At the quantum level, time behaves differently than in relativity. Quantum mechanics treats time as a fixed parameter, not a dynamic player. Reconciling this with relativity, which makes time flexible, remains one of the greatest challenges in physics. What is time, really? Is it fundamental, or is it merely a useful construct? Is it a stage upon which the universe plays out its events, or is it part of the play itself? The emotional resonance of these questions is powerful. Time is not just physics, it is memory, mortality, and meaning. We live our lives under its relentless march, watching loved ones age, watching ourselves change, feeling the finite nature of existence pressing against us. To imagine time as elastic, relative, even illusory, is to challenge the deepest part of what it means to be human. Are we bound to its flow, or are we participants in something larger, something timeless? As the camera sweeps across the swirling galaxies, each containing billions of stars born, burning, and dying across cosmic epochs, the voiceover reflects, for the stars, time is measured in billions of years. For us, it is measured in fleeting heartbeats. Yet both are woven into the same fabric. The same space. The same time. And then the haunting question, if time is an illusion, then what does it mean to say that we live, that we change, that we die? Are we moments in a story already written, or are we still writing the tale as we go? The section closes with the contrast that defines this mystery. Time is both utterly real and yet perhaps not real at all. It governs our every moment, yet dissolves under the scrutiny of physics. It flows inexorably forward, and yet may not flow at all. In its paradox, we glimpse the vast, unfathomable depths of the universe, and the fragile, fleeting beauty of our own existence within it. The cosmic microwave background, often called the afterglow of creation, is the oldest light in the universe, a silent whisper from nearly 14 billion years ago, still faintly echoing across the skies. To gaze upon it is to peer back to a time before stars, before galaxies, before even the structure of space had fully taken shape. It is the fossil light left over from the Big Bang itself, stretched thin and cooled by billions of years of expansion, now bathing the universe as a faint microwave glow. Though invisible to our eyes, it surrounds us completely, filling every corner of space like a ghostly reminder of the universe's fiery birth. This story begins in the earliest moments of the cosmos. For the first several 100,000 years after the Big Bang, the universe was a hot, dense soup of particles and radiation. Photons, the particles of light, could not travel freely because they constantly scattered off electrons and protons, trapped in an endless fog. The universe was opaque, like a seething fireball where light itself was imprisoned. But as the cosmos expanded and cooled, protons and electrons combined to form neutral atoms in a process called recombination. Suddenly, light was free to travel. The fog lifted. The universe became transparent for the very first time. And the photons released in that instant are still traveling today, stretched into microwaves by the expansion of space. These are the photons that make up the cosmic microwave background, or CMB. The discovery of the CMB was almost an accident. In 1965, Arno Penzias and Robert Wilson, working at Bell Labs in New Jersey, were experimenting with a radio antenna designed for satellite communication. They detected a faint, persistent noise that came from every direction in the sky, day and night. At first, they thought it was interference, perhaps from nearby cities, or even from pigeons nesting in their antenna. But after cleaning out the antenna and testing again, the noise persisted. What they had stumbled upon was nothing less than the leftover radiation from the Big Bang. Their discovery confirmed a bold prediction made years earlier by theorists, and it won them the Nobel Prize. More importantly, it offered humanity a direct glimpse into the infancy of the cosmos. The CMB is not just a relic, it is a treasure trove of information. It carries within it subtle patterns, tiny fluctuations in temperature, no more than a fraction of a degree, that reveal the seeds of all future structure in the universe. These fluctuations are like the faint fingerprints of the cosmos, the first whispers of the galaxies, stars, and planets that would eventually form. By studying them, scientists can reconstruct the conditions of the early universe with astonishing precision, learning about its composition, its age, and even its ultimate fate. When the Wilkinson Microwave Anisotropy Probe, WMAP, and later the Planck satellite mapped the CMB in exquisite detail, the results were both beautiful and humbling. The sky was revealed to be mottled with faint blue and red patches, representing slight variations in temperature and density across the infant universe. These tiny differences would, over billions of years, grow into the vast cosmic web of galaxies and clusters we see today. Without the primordial ripples captured in the CMB, the universe as we know it would not exist. The patterns in the CMB also tell us what the universe is made of. They confirm that ordinary matter, the atoms that make up stars, planets, and people, accounts for less than 5% of the total. The rest is dark matter and dark energy, unseen but essential. The CMB also gives us the most precise age of the cosmos, about 13.8 billion years. It is, in essence, the universe's birth certificate, written in faint microwave light. Yet, as with every great discovery, the CMB raises as many questions as it answers. Some anomalies in its patterns hint at mysteries beyond our current understanding. There are cold spots, unusually large regions with lower temperature than expected, that defy standard cosmological models. Could these be signs of vast voids in space, or hints of phenomena outside our observable universe? Some theorists even speculate that they could be scars left by collisions between our universe and others, a possible clue to the existence of a multiverse. The philosophical implications of the CMB are staggering. It is not just light from the past, it is the closest thing we have to a photograph of creation itself. When we look at the CMB, we are seeing the universe as it was when it was only 380,000 years old, a mere infant compared to its current age. It is a reminder that all of existence, from the galaxies to the Earth to ourselves, arose from that hot, dense beginning. We are, in a very real sense, children of the fireball. The imagery of the CMB carries a haunting beauty. Imagine standing beneath a night sky not filled with stars but with an invisible glow, stretching in every direction, a cosmic whisper older than any atom in your body. That glow is everywhere, passing through us even now, a silent chorus that has been singing since the dawn of time. To think that this ancient light still surrounds us is to feel both small and profoundly connected, to know that we are part of a story that began long before us and will continue long after we are gone. And so, the voiceover asks, if the cosmic microwave background is the first light, what came before it? What existed in those earliest, unlit moments, when even light itself was trapped? The question lingers, pulling the viewer toward the next great mystery, the unseeable dawn that preceded the universe we know, hidden not just in the fabric of space, but in the silence before light itself was born. Dark matter is one of the most haunting mysteries buried within the universe. Unlike stars that blaze with light or planets that reflect the glow of suns, dark matter does not shine, does not absorb, and does not emit radiation of any kind. It is invisible, a silent, shadowy presence woven through the cosmos. Yet, though it hides from our instruments, its influence is unmistakable. Galaxies spin too fast for their visible matter alone to hold them together. Light bends and arcs in ways that betray unseen mass. Vast cosmic structures, from filaments to clusters, owe their formation to a gravitational glue we cannot see. Dark matter is everywhere, and yet we do not know what it is. The first hints of dark matter emerged nearly a century ago. In the 1930s, Swiss astronomer Fritz Zwicky studied the Coma cluster, a massive assembly of galaxies. He found that the galaxies were moving far too quickly to be bound together by the visible matter alone. Something unseen, something he called dunkle materie, or dark matter, had to be holding the cluster together. Decades later, astronomer Vera Rubin's pioneering work on galactic rotation curves revealed the same truth on a smaller scale. Stars at the edges of galaxies were moving just as fast as those near the center, a motion impossible without an invisible halo of mass surrounding each galaxy. What Rubin uncovered was not an anomaly but a fundamental feature of the universe. Since then, evidence for dark matter has multiplied. Gravitational lensing, the bending of light by gravity, shows us arcs and rings of galaxies distorted by masses we cannot see. The distribution of the cosmic microwave background reveals how invisible matter sculpted the universe's earliest structures. Even computer simulations of galaxy formation only work when dark matter is included. Everywhere we look, the invisible hand of dark matter shapes the cosmos, silently dictating the architecture of everything we know. And yet, for all this evidence, the nature of dark matter remains an enigma. What is it made of? The simplest explanation is that it consists of some new kind of particle, beyond the familiar protons, neutrons, and electrons. Physicists have proposed candidates: WIMPs, weakly interacting massive particles; actions, sterile neutrinos. Entire experiments have been built deep underground to detect the rare collisions between dark matter particles and ordinary atoms. But so far, the silence continues. Billions of dollars, decades of research, and still the detectors wait for a signal that may never come. This absence forces us to confront unsettling possibilities. Perhaps dark matter is not a particle at all, but a sign that our theories of gravity are incomplete. Modified gravity theories attempt to explain the motions of galaxies without invoking invisible matter. While intriguing, most fail to match the wealth of evidence that points toward a hidden mass. Still, the possibility remains that the cosmos hides truths stranger than we imagine, that dark matter is not matter at all, but a crack in our understanding of the fundamental laws of nature. Philosophically, dark matter touches on something profound. It suggests that most of reality is hidden from us. Ordinary matter, the stars, the planets, the atoms in our bodies, makes up less than 5% of the universe. The rest is invisible. If our everyday experience is shaped by the rarest, most fragile fraction of reality, then what does that say about our place in the cosmos? We are inhabitants of a shadow universe, built atop unseen foundations. The imagery of dark matter is paradoxical: an invisible scaffold, a cosmic skeleton upon which all visible galaxies are hung. Imagine looking at the night sky and knowing that the glittering stars and glowing nebulae are only the faintest traces of a much larger, invisible structure. The galaxies are like lanterns hung upon an unseen web that stretches across the universe. Without that hidden web, the lanterns would scatter and drift apart, the universe dissolving into chaos. It is the unseen that holds everything together. And yet, dark matter is not only a scientific puzzle but also a narrative of pursuit. The hunt for dark matter is one of the great quests of modern physics, driven by both patience and obsession. Deep underground, detectors filled with liquid xenon or crystals of germanium sit in silence, waiting for the faintest ripple of interaction. In the skies, telescopes search for gamma rays that might betray the annihilation of dark matter particles. At particle colliders, scientists smash protons together in hopes of creating new forms of matter that could explain the invisible mass. Each experiment is like listening for a whisper in the storm, a whisper that could rewrite the story of existence. The contrast embedded in dark matter is striking. It is at once everywhere and nowhere, obvious and elusive, undeniable and invisible. This tension gives the mystery its power. To study dark matter is to chase a shadow, to wrestle with something that both shapes the universe and refuses to reveal itself. It is a cosmic ghost story, except the ghost is real, and without it, there would be no galaxies, no stars, no Earth, and no us. As the camera sweeps across the vastness of the universe, we see glowing filaments of galaxies tracing the great cosmic web. Between them, immense voids stretch out, dark and silent. Over this imagery, the narration presses the viewer with a haunting question: if most of the universe is invisible, then what is reality? Are we living inside a shadow world, surrounded by secrets we cannot touch? This is the hook that carries us deeper, from the unseen matter that holds galaxies together, to the even greater mystery that drives the expansion of the cosmos itself. If dark matter is the invisible hand that binds the universe, then dark energy is the silent force that tears it apart. Together, they form the unseen majority of reality, the ultimate secrets buried in the fabric of space. If dark matter is the hidden scaffolding of the universe, dark energy is the invisible hand that pushes it apart. While dark matter binds galaxies together, dark energy drives them away from each other, accelerating the expansion of the cosmos at a pace that has left scientists both awed and bewildered. It is a force without form, a presence without mass, a phenomenon that cannot be touched, seen, or directly measured. Yet its effect is undeniable. The universe is not just expanding, it is speeding up. The discovery of this mysterious energy has transformed our understanding of the cosmos and forced us to confront the possibility that the majority of reality is governed by something utterly incomprehensible. The story of dark energy begins in the late 1990s, when two independent teams of astronomers, studying distant Type Ia supernovae, made a discovery that shook the foundations of cosmology. These stellar explosions act as cosmic yardsticks, bright and consistent enough to measure distances across billions of light-years. Scientists expected to see the expansion of the universe slowing down under the influence of gravity. Instead, the supernovae revealed something far stranger: the universe's expansion was accelerating. Galaxies were moving away from each other faster and faster, a finding that directly contradicted centuries of assumptions about the cosmos. This invisible force driving the acceleration was dubbed dark energy. Unlike dark matter, which exerts a gravitational pull, dark energy works in opposition to gravity. It is repulsive, pushing galaxies apart and shaping the universe's destiny. The simplest explanation is the cosmological constant, an idea Einstein introduced as a mathematical term in his equations of general relativity. He originally conceived it to allow for a static universe, later calling it his greatest blunder when it was found that the universe was expanding. Yet today, the cosmological constant has returned as a leading candidate for dark energy, representing a persistent, uniform energy inherent to space itself. This energy is subtle, yet immense, permeating every corner of the cosmos and driving the galaxies ever farther apart. The scale of dark energy is staggering. It accounts for roughly 70% of the total energy in the universe, dwarfing the combined mass of visible matter and dark matter. To imagine it is to confront the vastness of the unknown. Nearly 3/4 of the cosmos is made of something we cannot touch, cannot detect directly, and barely understand. While we can observe its effects, we are profoundly limited in our ability to interact with or manipulate it. It is a force that shapes the universe on the grandest scales, yet remains completely beyond human experience. This invisible push raises profound questions about the ultimate fate of the universe. If dark energy continues to dominate, the cosmos will expand indefinitely, galaxies drifting ever farther apart, stars burning out, and the universe gradually cooling toward a distant, silent heat death. In this scenario, the vast structures we observe today, galaxies, clusters, the cosmic web itself, will become isolated islands in a darkening sea. Space will stretch beyond recognition, and the night sky, once teeming with stars, will fade into near emptiness. But there are other possibilities. Some theorists suggest that dark energy may be dynamic, not constant, a field that evolves over time, sometimes called quintessence. Its influence could strengthen, leading to the apocalyptic Big Rip, where galaxies, stars, planets, and even atoms are torn apart by the accelerating expansion. Alternatively, dark energy could weaken or vanish entirely, allowing gravity to regain dominance and potentially triggering a catastrophic collapse known as the Big Crunch. Each scenario paints a dramatically different picture of the cosmos, and the uncertainty only deepens the mystery. The discovery of dark energy is as much a philosophical shock as it is a scientific one. Humanity has long assumed that the universe is comprehensible, a machine governed by rules we can uncover. Dark energy, like dark matter before it, reminds us of the limits of our understanding. The majority of the cosmos is not only invisible but behaves in ways that challenge intuition and defy simple explanation. The universe is stranger, more complex, and more unknowable than we dared to imagine. Yet, in this vast mystery lies profound wonder. Dark energy connects the smallest scales to the largest, linking quantum fields, the nature of space itself, and the ultimate fate of everything. It is a reminder that the universe is not static, not passive, but alive with forces that shape reality in ways we have barely begun to understand. The interplay of dark energy and dark matter forms a dynamic tension. One binds, the other tears apart. One builds, the other accelerates. One is hidden, the other invisible. Together, they govern the architecture and evolution of the cosmos, unseen yet utterly essential. The imagery of dark energy is haunting. Imagine galaxies drifting through a vast, silent ocean, carried along by a force we cannot perceive. Filaments of the cosmic web stretch into the darkness, pulled taut by the unseen hand of expansion. Stars and clusters recede, fading gradually into a universe that is both familiar and alien. It is a vision of beauty and desolation intertwined, a reminder that the cosmos is at once awe-inspiring and incomprehensible. And yet, the search for understanding continues. Observatories measure supernovae and galactic motions, satellites map the expansion rate of the universe, and theoretical physicists explore possibilities ranging from modifications of gravity to exotic quantum fields. Each discovery peels back a layer of mystery, yet new questions emerge. What is the true nature of dark energy? Why does it exist in the quantity we observe? How will it shape the universe in the eons to come? These questions drive some of the most ambitious experiments and the deepest contemplation in modern science. The emotional impact of dark energy lies in its contrast with human perception. We live our lives in a universe that feels stable, slow, and ordered, yet on the grandest scales, space itself is stretching, accelerating outward at a rate beyond imagination. The cosmos is alive with forces we cannot see or control, a reminder of both the power and fragility of our place in existence. In the presence of dark energy, we confront the sublime, the tension between comprehension and mystery, between what we can measure and what we can only feel. As the narration closes, the viewer is left with a profound question. If the majority of the universe is invisible, pushing and shaping reality in ways we cannot perceive, then what is our place within it? Are we observers, participants, or mere spectators in a cosmos that exists far beyond our understanding? The concept of the multiverse stretches the boundaries of imagination and science alike. For centuries, humans have looked to the night sky and wondered if our universe, vast, intricate, and seemingly infinite, is the only one. Modern physics suggests that it may not be. Instead, our universe could be just one of countless others, each with its own laws, its own dimensions, and its own version of reality. This idea challenges the very notion of existence, forcing us to reconsider what we mean by everything and what it truly means to inhabit a single universe. The idea of multiple universes emerges from several branches of theoretical physics. One of the earliest is the concept of cosmic inflation. Shortly after the Big Bang, the universe underwent an extraordinary expansion, growing exponentially in a fraction of a second. In some models, this inflation does not stop uniformly across space. While our observable universe stabilized and cooled, other regions could have continued inflating, forming separate bubble universes with their own distinct properties. Each bubble could possess different physical constants, different forms of matter, or even different dimensions, forming a vast multiverse where every possibility is realized somewhere. Quantum mechanics provides another pathway to the multiverse. The many-worlds interpretation, proposed by Hugh Everett in the 1950s, suggests that every quantum event spawns a new branch of reality. When a particle exists in a state of probability, the universe splits to accommodate each possible outcome. In this framework, every choice, every random fluctuation, every cosmic accident gives rise to a parallel universe. Somewhere, in an infinite expanse of possibilities, another version of you is reading this script, another version of the Earth is spinning in a slightly altered orbit, and another version of the cosmos unfolds according to its own set of events. The universe is not singular but a boundless tree of branching realities. The multiverse challenges our intuition in profound ways. If there are infinite universes, then every conceivable version of reality exists somewhere. A universe where gravity is weaker, a universe without atoms, a universe where life never emerges. Conversely, every unlikely event, every fluke, every miracle we experience might exist countless times over across the multiverse. This shifts our understanding of probability, destiny, and the nature of existence itself. What we consider improbable or extraordinary in our universe may be inevitable in another. Observational evidence for the multiverse is elusive, but tantalizing hints exist. Some anomalies in the cosmic microwave background, faint cold or hot spots, have led scientists to speculate about collisions between our universe and neighboring ones. Certain patterns in the distribution of galaxies or the fine-tuning of physical constants suggest that our universe may be one bubble in a far larger cosmic foam. Yet these hints are indirect, often speculative, and subject to rigorous debate. The multiverse remains as much a philosophical idea as a scientific hypothesis, straddling the line between imagination and empirical inquiry. Philosophically, the multiverse forces us to confront existential questions. If infinite versions of reality exist, what does that mean for individuality, free will, and identity? Are our lives unique, or just one of countless iterations across the cosmic expanse? Does meaning depend on the rarity of events, or is meaning itself diluted when every possibility is realized somewhere? These are questions that challenge not only science but the very way we understand ourselves. The imagery of the multiverse is both sublime and disorienting. Imagine an infinite gallery of universes, each glowing like a bubble in a cosmic foam, stretching endlessly into the void. Some shine brightly, filled with stars and galaxies, others remain dark and barren, devoid of matter or light. Each is a self-contained cosmos, a universe unto itself, spinning out possibilities beyond comprehension. The sheer scale is staggering. If even a fraction of these universes exists, the totality of reality is vastly greater than anything our senses can perceive. The multiverse also reframes our understanding of the fine-tuning of our universe. The physical constants that govern gravity, electromagnetism, and nuclear forces are precisely balanced to allow for stars, planets, and life. In a multiverse, this fine-tuning might not be mysterious. We exist in one of the universes where conditions happen to allow observers like us to arise. In other words, the multiverse offers a potential explanation for why the cosmos seems so exquisitely tuned for life. We could not exist in a universe that does not permit us. Yet, even as the multiverse offers answers, it raises deeper mysteries. How many universes exist? Are they infinite, or merely vast beyond imagination? Can they ever interact, or are they eternally isolated? And if they are inaccessible, is the multiverse truly a scientific idea, or a philosophical one? These questions blur the boundaries between physics, metaphysics, and cosmology, creating a space where human curiosity meets the limits of comprehension. Emotionally, the multiverse evokes awe and vertigo. It is a concept that humbles the mind, forcing us to confront the possibility that the universe we inhabit is only one thread in an infinite cosmic tapestry. It blends wonder with unease, the recognition of our smallness, the thrill of possibility, and the haunting realization that reality may be far stranger than we can ever fully perceive. As the camera pans outward from our Milky Way, the narration guides the viewer through an imagined landscape of countless universes, glowing and spinning in the void, a silent, infinite chorus of creation. The voiceover asks, if there are infinite versions of reality, each playing out its own story, then what does it mean to exist? Are we alone, or are we one of infinite lives in an endless cosmic symphony? The multiverse, with its infinite possibilities and boundless mysteries, is a reminder that the cosmos extends far beyond what we can observe or measure. It is the ultimate contrast, a universe both comprehensible and incomprehensible, intimate in its reflection of our own existence and vast beyond imagining. And it leaves us with a haunting, exhilarating question. If reality is infinite, what role do we play in its endless unfolding? Wormholes are perhaps the most tantalizing and cinematic of all theoretical constructs in the universe, bridging the realms of science, imagination, and philosophy. They are hypothetical passages through the fabric of spacetime, tunnels that could connect distant points in the cosmos instantaneously, or even link different universes. To envision a wormhole is to imagine folding a sheet of paper so that two distant points touch, creating a shortcut through an otherwise vast expanse. The idea is not mere fantasy. It emerges naturally from Einstein's theory of general relativity, which allows for solutions in which spacetime curves back on itself. Yet, as beautiful and dramatic as the concept is, wormholes remain hypothetical, existing at the edge of theory where physics flirts with the limits of comprehension. The origins of the idea trace back to the early 20th century. In 1935, Albert Einstein and Nathan Rosen formulated what became known as the Einstein-Rosen bridge, a theoretical connection between two separate points in spacetime. This bridge could, in principle, create a shortcut, though they initially considered it more a mathematical curiosity than a practical pathway. Later, physicists like Kip Thorne explored the possibility of traversable wormholes, considering the requirements for stability and the exotic matter needed to keep such a tunnel open. To maintain a wormhole, negative energy would likely be required, a type of matter that behaves in ways completely unlike anything we experience on Earth, repelling gravity rather than succumbing to it. The implications of traversable wormholes are staggering. They could, theoretically, allow instantaneous travel across galaxies, bypassing the light years of space that would otherwise separate stars and planets. Beyond that, some models suggest that wormholes might connect not just distant regions of our universe, but entirely separate universes, offering a bridge into realms with different physical laws, constants, or even timelines. In this way, wormholes are not just cosmic highways, they are portals into the ultimate unknown. Yet the theoretical elegance of wormholes collides with formidable challenges. Stability is the first and most obvious hurdle. Without negative energy or some form of exotic matter, a wormhole would collapse the moment it formed, crushing anything that tried to pass through. The quantum foam at the smallest scales of spacetime adds another layer of uncertainty. Fluctuations in energy could destabilize the tunnel, making it vanish before anything could traverse it. Even if a stable wormhole could exist, there is the problem of causality. Some solutions allow for time loops, raising paradoxes such as the grandfather paradox, where events could influence their own past in ways that defy logical consistency. Despite these challenges, wormholes capture the imagination in ways few other phenomena can. They are the embodiment of contrast, a structure both terrifying and inviting, a potential pathway to discovery and destruction alike. They evoke awe because they suggest that distance, the vast emptiness of space, might not be absolute. They provoke fear because the conditions required to traverse them are extreme, the risks unimaginable. To contemplate a wormhole is to confront the strange interplay of possibility and peril, of physics and philosophy intertwined. Wormholes also serve as a profound metaphor for our understanding of the universe. They are an illustration of how the cosmos is more flexible, more interconnected, and stranger than our senses suggest. While stars blaze in predictable patterns and planets follow measurable orbits, the deep structure of spacetime could be folded, twisted, and punctuated by unseen tunnels. This unseen architecture, invisible yet theoretically plausible, hints at a universe that is not only vast, but profoundly dynamic, where shortcuts and bridges may exist beyond our perception. The imagery of a wormhole is cinematic in the truest sense. Imagine a swirling tunnel of light and shadow, twisting through the void, its mouth surrounded by stars distorted and stretched by the intense gravitational curvature. Matter and energy spiral toward the throat, warping time and bending light into impossibly beautiful arcs. One could peer into the distant universe or into an entirely alien cosmos through this corridor, witnessing landscapes and skies that defy imagination. It is a vision that is both alluring and terrifying, a gateway to discovery fraught with risk. Philosophically, wormholes raise deep questions about space, time, and existence itself. If they are possible, then distance is not a fundamental barrier, and the concept of causality may be more flexible than we assume. Could humanity one day traverse these cosmic bridges? Could we reach distant galaxies, or even alternate realities, in ways that defy the speed of light? Or are wormholes destined to remain theoretical constructs, reminders of the universe's strangeness rather than practical pathways? These questions hover at the boundary of science and imagination, challenging both our understanding and our audacity. Emotionally, wormholes evoke a unique blend of wonder and vertigo. They confront us with the scale and mystery of the cosmos, simultaneously suggesting that the universe is navigable and that it may harbor perils beyond comprehension. They are a symbol of the unknown, the ultimate contrast between human curiosity and cosmic indifference. In contemplating a wormhole, we confront the possibility of instantaneous connection across space, yet also the terrifying reality that such a passage may be unstable, destructive, or entirely beyond reach. As the narration guides the viewer through a visual depiction of a wormhole, the stars swirl into spirals of light, the horizon warping as the tunnel stretches into an impossible distance. The voiceover poses a haunting question: if a doorway exists between here and the farthest reaches of space, or even to another universe entirely, would we have the courage to step through? Or would the very act of crossing unravel the fabric of reality itself? In the end, wormholes remain one of the most evocative and compelling ideas in cosmology. They are a bridge between imagination and physics, a reminder that the universe is not merely a collection of stars and galaxies, but a dynamic, mysterious, and profoundly strange reality. They challenge our perception of space, time, and possibility, offering a glimpse of what might lie beyond the limits of experience and understanding. Cosmic strings are among the most extraordinary and enigmatic ideas in modern physics, hypothetical remnants from the earliest moments of the universe. Unlike stars or black holes, they are not made of matter in any conventional sense. Instead, cosmic strings are thought to be one-dimensional defects in the fabric of spacetime itself, infinitesimally thin but stretching across unimaginable distances, potentially longer than entire galaxies. They are relics of symmetry breaking during the universe's birth, leftover threads from the searing chaos of the Big Bang, frozen in the structure of reality. If they exist, they could carry enormous energy, warp space, and even leave observable imprints on the cosmic microwave background. To contemplate cosmic strings is to peer into a universe stitched together by invisible threads, to imagine the architecture of spacetime itself as a tapestry of hidden tension and power. The theoretical foundations of cosmic strings emerge from particle physics and cosmology. During the first fractions of a second after the Big Bang, the universe cooled rapidly, undergoing a series of phase transitions similar to water freezing into ice. In this process, the fundamental forces and fields of nature separated, and topological defects could form, cosmic strings being one-dimensional examples of such defects. Unlike ordinary matter, These strings are made of pure energy and tension, a concentration of the universe's primordial forces compressed into a thread thinner than a proton but immensely powerful. The tension within a cosmic string could be so great that a single centimeter of string would have the energy equivalent to Mount Everest compressed into it. Cosmic strings, if they exist, could have profound effects on the cosmos. Their immense mass energy would warp spacetime around them, creating gravitational lensing effects capable of bending light from distant galaxies into arcs or double images. In some models, strings could even generate gravitational waves, ripples in spacetime, that might be detectable with instruments such as LIGO or future space-based detectors. Observing these effects would not only confirm the existence of cosmic strings but also provide an unprecedented window into the physics of the early universe, revealing conditions and forces that existed only moments after the Big Bang. The observational hunt for cosmic strings is ongoing but challenging. So far, no definitive evidence has been found, though scientists continue to search for subtle distortions in the cosmic microwave background, unusual gravitational lensing patterns, or signatures in gravitational wave data. Detecting a cosmic string would be like discovering a scar from the universe's birth, an ancient mark left by processes that shaped everything we see today. It would connect the present cosmos to its fiery, chaotic beginnings, offering a bridge across time and space. The philosophical implications of cosmic strings are profound. They suggest that the universe is not smooth or uniform, but structured by invisible threads and defects that carry the memory of creation itself. Reality, in this view, is a complex web, stitched together by the fundamental forces and topological quirks born in the first moments of existence. The cosmos is not just a stage where matter and energy perform, but a dynamic, textured fabric with a hidden architecture, revealing that what we perceive is only a fraction of a deeper, more intricate reality. The imagery of cosmic strings is haunting and cinematic. Imagine a vast expanse of space with a thread thinner than light, stretching endlessly across the void. Around it, starlight bends subtly, galaxies appear duplicated or warped, and a faint shimmer of gravitational waves pulses outward like ripples on a cosmic pond. These strings are both elegant and unsettling, delicate in width, yet unimaginably powerful, hidden in plain sight yet capable of shaping the structure of the universe itself. The very fabric of spacetime trembles under their tension, a visual metaphor for the hidden forces that govern reality. Cosmic strings also embody the interplay of contrast and tension. They are at once invisible and immensely massive, minuscule in width yet vast in length, remnants of chaos that have persisted into the orderly universe we see today. They are silent witnesses to creation, yet could unleash energy and forces beyond imagination. In contemplating them, we are reminded of the universe's duality, beauty intertwined with danger, order emerging from chaos, the seen underpinned by the unseen. The potential significance of cosmic strings extends beyond mere curiosity. If they exist, they could answer some of the deepest questions in cosmology, including how structure formed in the early universe, the unification of fundamental forces, and the behavior of spacetime under extreme conditions. They would be tangible evidence of phenomena that occurred at energy scales far beyond the reach of Earth-based experiments, offering a direct glimpse into the earliest moments of reality. In essence, they could provide a roadmap to the physics of creation, a way to understand how the universe evolved from a formless, searing energy soup into the cosmos we inhabit today. Emotionally, cosmic strings evoke both awe and vertigo. They suggest that the universe is not a static, homogeneous void but a living, dynamic fabric, threaded with invisible structures that carry the weight of creation. They remind us that reality is stranger and more intricate than our senses reveal, that we exist within a cosmos that preserves the memory of its own violent birth. To imagine these strings is to feel both small and connected, part of a universe that is at once elegant, terrifying, and unimaginably vast. As the camera pans across an imagined cosmic landscape, faint threads stretch across the darkness, bending starlight and whispering of the universe's hidden structure. The narration lingers. If the universe is stitched together by threads invisible to the eye, then what secrets lie hidden in the fabric of reality? Are we merely passengers upon a tapestry of cosmic tension, or are these strings guiding the very evolution of existence itself? Cosmic strings remain theoretical, yet their potential existence illuminates the extraordinary depth and complexity of the cosmos. They are not merely relics of the past, they are bridges between what we see and what we cannot, threads connecting our present to the universe's fiery origin. In contemplating them, we confront the invisible architecture of reality, a hidden structure that shapes the universe on scales both unimaginably vast and profoundly intimate. The concept of time travel has long captivated the human imagination, from the pages of science fiction to the corridors of theoretical physics. It is a notion that stretches the boundaries of reality, challenging our understanding of causality, destiny, and the very nature of existence. Time travel is not merely the stuff of novels or films, it emerges naturally from the laws of physics, particularly through Einstein's theory of general relativity. In the warped fabric of spacetime, the possibility exists, at least theoretically, to move forward or backward along the timeline, navigating the universe in ways that defy our everyday experience. To contemplate time travel is to confront the paradoxical nature of reality itself, where past, present, and future intertwine in ways both tantalizing and terrifying. The theoretical foundation for time travel lies in the curvature of spacetime. According to general relativity, massive objects bend the fabric of space and time around them. In extreme cases, this curvature can become so pronounced that closed time-like curves are possible, paths through spacetime that loop back on themselves. Wormholes, which we have explored earlier, are one such possibility. If a traversable wormhole connects two regions of spacetime, and one mouth is accelerated to near-light speed or placed in a strong gravitational field, the difference in time experienced at each end could, in principle, allow a traveler to move backward or forward in time relative to an outside observer. This is not mere speculation, it is a direct consequence of Einstein's equations. Yet the physics of time travel is riddled with paradoxes and challenges. The grandfather paradox, for example, asks, if a person travels back in time and prevents their own ancestor from meeting a partner, would they cease to exist? This type of causal loop seems logically impossible, yet the equations of general relativity allow solutions where such loops might occur. Some physicists propose that the universe protects itself through consistency constraints, meaning that any actions a time traveler takes were always part of history. Others invoke the many worlds interpretation of quantum mechanics, suggesting that traveling back in time creates a new branch of reality, leaving the original timeline unchanged. Each explanation is as mind-bending as it is speculative, highlighting the tension between possibility and logical coherence. Time travel also forces us to confront the nature of causality itself. In our everyday experience, causes precede effects. We flip a switch, and a light turns on. We plant a seed, and a tree grows. But in a universe with time loops, causality can become circular, effects can precede causes, and the linear narrative of events dissolves. This challenges our deepest intuitions about reality, leaving us to question whether time is a river flowing in one direction or a malleable fabric that can twist, fold, and loop upon itself. The very notion of free will becomes entangled with physics, as our choices might be constrained by the structure of spacetime in ways we cannot perceive. The possibility of time travel also intersects with quantum mechanics. At the subatomic level, particles exist in states of probability, and their paths are not determined until measured. Some physicists speculate that quantum effects could allow microscopic time loops, virtual journeys backward and forward in time, though scaling such effects to macroscopic objects remains far beyond current understanding. Quantum mechanics introduces a further layer of uncertainty and complexity, suggesting that time travel may not only be paradoxical but probabilistic, a dance of chance and possibility that defies classical intuition. The imagery of time travel is both exhilarating and haunting. Imagine stepping through a portal into a past era, seeing continents in different configurations, witnessing stars in unfamiliar constellations, or encountering civilizations long vanished. Alternatively, one could peer into the far future, observing the death of stars, the fading of galaxies, and the slow cooling of the universe toward a distant heat death. The visual possibilities are limitless, yet they carry an emotional weight, the thrill of exploration entwined with the disorientation of encountering a reality untethered from the familiar flow of time. Philosophically, time travel forces us to confront questions of existence, responsibility, and destiny. If the future can be seen, is it fixed, or can it be changed? If the past can be altered, what becomes of memory, identity, and consequence? Time travel challenges the notion of a singular, linear self, suggesting instead a universe of overlapping possibilities, where history is malleable and reality is a tapestry of interwoven timelines. This perspective reshapes our understanding of life itself, inviting us to see existence not as a sequence of moments but as a multidimensional continuum, rich with potential and peril. The emotional resonance of time travel is profound. It evokes awe at the scale and complexity of the universe, fear of the consequences of altering events, and wonder at the freedom of moving through eras as if navigating a boundless ocean. It combines human curiosity with cosmic mystery, creating a tension between knowledge and danger, between possibility and limitation. To imagine traveling through time is to confront the ultimate contrast, the smallness of human experience against the infinite backdrop of spacetime, the fragility of life against the immensity of the cosmos. Time travel also underscores the interconnectedness of the universe. Past, present, and future are not separate realms but threads woven into the same cosmic fabric. Actions in one moment can ripple across time, and events separated by eons may be bound by invisible connections. This interconnectedness mirrors the larger structures we have explored: black holes, cosmic strings, dark energy, suggesting that time itself is part of the same intricate architecture that governs space, matter, and energy. As the camera pans across a visual representation of a time travel corridor, stars stretch into elongated streams of light, galaxies twist into impossible shapes, and a shimmering tunnel bends reality around it. The narration poses a haunting question: if we could travel through time, would we merely witness the past and future, or would we become actors in a story already written? Could we change destiny, or is every moment inevitable, locked in the fabric of spacetime? Time travel, with all its theoretical intrigue, philosophical weight, and cinematic grandeur, remains one of the most compelling concepts in modern physics. It challenges our understanding of causality, existence, and the very nature of reality. Whether ever achievable or forever theoretical, it invites us to imagine a universe far stranger and more intricate than our ordinary perceptions allow, a universe where time is not a line but a landscape, and where the limits of possibility stretch as far as the imagination can reach. The ultimate destiny of the universe is a question that has fascinated scientists, philosophers, and dreamers alike for centuries. As we peer deeper into the cosmos and unravel its hidden laws, we are forced to confront not only the mechanics of its evolution but also the haunting question of its end. Will the universe continue to expand forever, drifting into a silent, frozen oblivion? Will it collapse back on itself in a cosmic implosion? Or could something even stranger await, a fate beyond our imagination? The study of the universe's end is both scientific inquiry and philosophical meditation, blending mathematics, observation, and awe into a contemplation of existence itself. Current evidence suggests that the universe is dominated by dark energy, the mysterious force accelerating cosmic expansion. Galaxies are moving away from each other at increasing speeds, and space itself stretches relentlessly. If this trend continues, the universe may face a scenario known as the heat death or the big freeze. In this distant future, stars will burn out, galaxies will drift apart, and all thermodynamic processes will slow to a halt. The cosmos will grow darker, colder, and emptier, leaving a vast expanse of near-perfect equilibrium, a silent testament to the passage of time. Life, as we know it, would become impossible, and the universe would enter a state of eternal, unchanging stillness. Yet the fate of the cosmos is not predetermined. Alternative scenarios have been proposed, each with its own dramatic implications. The Big Crunch suggests that if dark energy diminishes or reverses, gravity could eventually overcome expansion. Galaxies would converge, stars would collide, and the universe would collapse inward, culminating in a singularity, a point of infinite density and temperature. This reversal of cosmic history would be violent, obliterating everything in a cataclysmic finale, yet it also opens the possibility of cyclic cosmologies, where a new universe could emerge from the remnants of the old, reborn in a perpetual cycle of creation and destruction. More speculative ideas push the boundaries of imagination further still. The Big Rip scenario envisions a universe where dark energy grows ever stronger, tearing apart galaxies, stars, planets, and even atoms themselves. In this ultimate dissolution, the very fabric of spacetime would be ripped asunder, leaving a universe devoid of structure, order, or coherence. In other models, quantum fluctuations could trigger phase transitions in the vacuum of space, radically altering the laws of physics and transforming reality in ways that are almost impossible to visualize. These possibilities underscore a sobering truth: the universe's end may be as strange and unpredictable as its beginning. The search for answers combines observational astronomy, theoretical physics, and cosmology. Telescopes measure the rate of expansion, mapping distant supernovae and galaxies to refine estimates of the Hubble constant. Satellites analyze the cosmic microwave background, revealing subtle clues about the universe's composition, structure, and evolution. Particle accelerators probe fundamental forces, searching for hints about dark energy, dark matter, and the vacuum itself. Each piece of evidence brings us closer to understanding the ultimate trajectory of existence, yet each also opens new questions, highlighting the limits of human knowledge and the vastness of the unknown. Philosophically, the universe's potential fates challenge our perception of time, existence, and meaning. Humans live within the fleeting moments of a single star, a tiny blink in the cosmic clock. Yet we are capable of contemplating billions of years, of imagining an existence long after our sun has burned out and our galaxy has drifted into darkness. This perspective evokes both humility and wonder, reminding us that we are simultaneously insignificant and profoundly connected to the vast tapestry of reality. The universe's end is not just a scientific question, it is a meditation on impermanence, on the fragility of life, and on the transient beauty of existence itself. The imagery of the universe's destiny is hauntingly cinematic. In the Big Freeze, galaxies fade into faint smudges, stars dim into obscurity, and space stretches into a cold, silent void. In the Big Crunch, galaxies swirl violently toward a central point, matter collapsing into intense brightness before disappearing into singularity. The Big Rip portrays stars torn apart, cosmic filaments stretched like taffy, and space itself fracturing into chaos. These visions combine awe, terror, and beauty, providing a striking contrast between human perception and the unfathomable scale of cosmic processes. The universe's end also invites reflection on our own temporality. Just as stars and galaxies have lifespans, so too does human existence occupy a finite interval. Contemplating the cosmos' ultimate fate magnifies the preciousness of our own lives and experiences, reminding us that meaning is created in moments, that beauty arises in fleeting flashes, and that understanding is always partial. The final fate of the universe mirrors our own mortality, a cosmic parallel that evokes both melancholy and reverence. In considering the ultimate destiny of the universe, we confront the sublime, the simultaneous grandeur and indifference of reality. The universe evolves according to laws vast and impersonal, yet within that framework, life emerges, consciousness awakens, and questions are asked. We are small, yet capable of grasping concepts that span billions of years and trillions of miles. This duality, of human significance against cosmic scale, defines the emotional resonance of the universe's end. As the camera drifts through a visualization of the cosmos' possible futures, the narration poses a haunting question. If the universe is destined to fade, collapse, or tear itself apart, what meaning does existence hold? Are we witnesses to a story already written in the stars, or do our lives ripple outward, leaving echoes in a cosmos that stretches far beyond comprehension? The ultimate destiny of the universe is not a closed chapter but an open question, a mystery that invites contemplation, exploration, and wonder. It reminds us that even as we probe the deepest laws of physics, the cosmos retains its majesty, complexity, and mystery. It is both an ending and an invitation, a call to understand, to imagine, and to appreciate the extraordinary tapestry of space, time, and life in which we are entangled.